introduction. First of all, I would like to express my sincere thanks to Axel and Raphael for organizing this very nice symposium. And I would like to talk about the asymmetric autocatalysis and origin of chirality. Yesterday, when Professor Biedma told me that when he looked into our website, he found our group members only two, myself and Dr. Kawasaki. So first I would like to show the picture of about 20 people. This is myself, and he is Dr. Kawasaki in the audience, and we owe a lot Dr. Kawasaki for the achievement. And we organized the Symposium on Molecular Chirality 2007 last year, and we invited Professor Joseph Ribo to Tokyo. And I'd like to talk only about only one reaction, and because the background of the audience may be broad, let me just remind you the concept of the reaction, osmotic reaction. I'm going to talk about the addition of alkyl metal reagent to aldehyde, R1COH. Aldehyde form, shape of aldehyde is just flat on the plane, and when the alkyl metal is polarized, alkyl is delta plus, delta minus, and metal is delta plus, and carbon is delta plus, oxygen is delta minus. When the alkyl metal approaches from the right side, called rephase, and then the carbon-carbon bond formation occurs, and after hydrolysis you will get secondary alcohol with absolute configuration. When R1 is phenyl, that is benzaldehyde, and methyl vinyl, you will get alcohol with R absolute configuration. And on the other hand, when the alkyl metal reagent approaches from the other side, C phase, you will get this secondary alcohol. Those are enantiomers, mirror images, and this is S. And without chiral material or chiral catalyst, the probability of the approach from the rephase and C phase is 1 to 1. When the number of molecules is very large, the ratio of S and R secondary alcohols is 1 to 1. That is the racemic. We always get racemic compound. And when we use the chiral catalyst, we can control the probability of the approach from the rephase, either or C phase. And then we can get the enantiomer-enriched secondary alcohol. That's the concept, the reaction. And as to the enantioselective addition of diethyl zinc, alkyl zinc, diethyl zinc to benzaldehyde, we have developed these chiral beta amino catalysts. That is the diphenyl N-methylfluorinol and also N-dibutyl norepinephrine. Those are highly enantioselective chiral catalysts. And when I go back, when I was still in I was a graduate student at Mukayama's laboratory. That's 1979, many years ago, that we observed that in the presence of this beta amino alcohol derivative, diethyl zinc acts to benzaldehyde, and we got 1-phenylpropanol with 76% synthetic yield. But unfortunately, the yield with this chiral ligand is almost zero. But still, the carbon-carbon bond formation occurs in the presence of beta amino alcohol. And then after that, Oguni and Onori reported, and we independently reported these chiral catalysts. And the reason that the amino alcohol accelerates the reactivity, nucleophilicity of dialkyl zinc can be explained as follows. The shape of dimethyl zinc is straight, with the bond length between zinc and carbon atoms 0.195 nanometer. When zinc atom is coordinated with other two nitrogen atoms, this is the X-ray taken from this, the bond angle carbon zinc, carbon becomes 145, bent 145 degree. At the same time, bond length between carbon and zinc atoms becomes longer, 0.198 nanometer. This means this delta minus, this means this nucleophilicity of this methyl methyl moiety is increased and enough to add to the carbon atom of aldehyde. And also recently, Professor Håkansson, Göteborg, reported the X-ray crystallography of the complex of the diisopropyl zinc and TMETA. Again, so the bond and become different. We use a lot of diisopropyl zinc later. So I'm going to talk the asymmetric autocatalytic reaction. The reaction, asymmetric autocatalysis, means the structures of the chiral catalyst and the products are the same. That means the chiral product acts as a chiral catalyst for its own production with the same absolute configuration. So in other words, the process is auto-multiplication of chiral compounds. And this type of reaction, asymmetric autocatalysis, has several advantages of the usual asymmetric catalysis because the process is auto-multiplication, so the efficiency is high, and also that there's no decrease in the amount of the reactivity of the catalyst because during the reaction the amount of catalyst increases. In other reactions, even if the chiral catalyst can be recovered in 99% EE, but the amount and also the reactivity is decreasing a bit. And also because the structures of the product and the catalyst are the same, so there is no need to separate the product from the catalyst. And also this is atomic economy proposed by atomic economy Professor Frost. In autocatalysis, starting material A and B and also P or 3 is enough usually, and in usual chiral catalyst A, B, and C, different compound is necessary. So this also the method. And while we were examining the enantioselective addition of dialkyl zinc to aldehydes, we once used pyridine-free carbaldehyde, nicotine aldehyde, instead of benzaldehyde. And we observed that reaction with this aldehyde proceeds rather fast. That means that within 1 hour at 0 degree. With the benzaldehyde catalyzed by NN-dibutyl it takes 16 hours. So we thought the product in situ, that means all zinc isopropyl, zinc alkoxide, can catalyze, can act as a catalyst. So we use this pyridyl alkanol with S configuration as a catalyst, autocatalyst, and the reaction between diisopropyl zinc and pyridine carbaldehyde gave also the S pyridyl alkanol. This was published in 1990, and we claimed that the predominant structure of the predominant product is the same. This one is the first asymmetric autocatalyst. But unfortunately, the enantiomeric excess of the newly formed product is lower than the parent chiral catalyst. But still, this is the first example. And after this, we made a lot of effort to find a more efficient system. And in the end of 1995, we finally found that this pyrimidine alkanol, just put one more nitrogen atom, pyrimidine alkanol with 93 or 95% enantiomeric excess, these are highly efficient asymmetric autocatalysts for the addition of diisopropyl zinc to pyrimidine 5-carbaldehyde. And the newly formed product had the enantiomer excess is of 90 to 96%. So the enantiomeric excess did not decrease. So the equimolar amount of diisopropyl zinc and pyrimidine alkanol reacts to form zinc monoalkoxide, and this acts as asymmetric autocatalyst and to form itself. And after hydrolysis, the increased amount of pyrimidine alkanol was obtained. And we examined in detail the effect of the substituent at the second position, this position, and we found that this alkynyl acetylenic bond is very efficient. And you see this alkynyl pyrimidine alkanol with greater than 99.5, essentially enantiopure alkanol, acts as an asymmetric autocatalyst for the addition of diisopropyl zinc to alkynyl pyrimidine carbaldehyde, and the synthetic yield is greater than 99, and the enantiomeric excess, that is the mixture of the initial catalyst and the product, is greater than 99.5. Then we use this product as an autocatalyst for the next round. Then again, and we repeated the reaction, and even after the 10th round, the yield is greater than 99, and also the enantiomeric excess is greater than 99.5. So there's no decrease in the reactivity and enantioselectivity of this in this asymmetric autocatalyst. So this is practically perfect asymmetric autocatalytic reaction result. And as was nicely presented by Professor Kagan, and this very important paper published in 1986 that told this influenced us very much because the non-linear effect, the enantiomeric excess of the product is higher than that of the chiral catalyst. And he reported asymmetric epoxidation, and also that Ogni reported this effect in alkylation or addition of diethyl zinc to benzaldehyde. He used this beta amino alcohol with 11% EE, and he obtained 1-phenyl propanol with the increased EE of 82. And when he used 3% EE, he obtained the increased EE of 36. And Noyori examined the mechanism in detail. And so, but this is not autocatalytic process. That means that even when the enantiomeric excess of the product is increased than that of the chiral catalyst from 3 to 36, once the reaction was stopped, so this 36% E cannot be increased further. So in our reaction, our reaction should be asymmetric autocatalytic system. So we examine the possibility of asymmetric amplification. And here, this is the first example that when I show here with R1 is hydrogen without substituent. When we use the asymmetric autocatalyst with 2% EE, 2% EE is the mixture of 51 to 49. This is the S enantiomer, and we did the reaction, and we got the increased amount of pyrimidine alkanol. This is a mixture of the initial autocatalyst and the product, and the EE was increased to 10 from 2 to 10. From 2 to 10 is not significant, but the important point is that this pyrimidine alkanol with 10% EE can be used as an asymmetric autocatalyst for the next round. So from 10 to 57 and 57 to 81 and 81 to 88. And with this substance, when we use the autocatalyst with 88% EE, so the newly product also the same enantiomeric excess. So these overall procedures means that starting from 2% EE amplification, from 2 to 88% was achieved. But the important point is without the assistance of any other chiral material. Just the initial imbalance of the substance is enough. This is the very essentially different point, important point. So this means we started from 2% E, but so we examined the asymmetric amplification from extremely low enantiomer excess. This is an example. This 2-alkyl pyrimidine alkanol with 0.00005% enantiomeric excess with S enantiomer. The first reaction gave the 2-alkyl pyrimidine alkanol with the increased in yield 57% yield. So it's really low to 57 enantiomeric excess increase. And then by using this alkanol with 57, the second round gave 99, and the third round gave greater than 99.5% EE. So during these 3 consecutive asymmetric autocatalysis, the initial slightly major S isomer has auto-multiplied by 630,000 times, while the minor less than 1,000. So this is the this E is extremely low. We cannot measure, but we prepared as follows. We synthesized racemic compound and we measured the weight, 0.13 to 3 millimole, and then to this we put enantiopure S-alkanol with the calculated amount. This one 1.610 minus 7 millimole. This makes the mixture of the racemic 100 and S enantiomer 0.00005. So the enantiomeric excess is approximately 0.00005% E. In a similar manner, we prepare our enantiomer. And of course, before this reaction, we examined carefully, step by step, first 5% E, then 0.5%, 0.05, and 0.005, and we reached this one. And also, we examined the opposite enantiomer. Again, so by 3 consecutive reactions, the E became greater than 99.5. And then, so this is the summary of it. This 2-alkyl pyrimidine alkanol is almost a perfect asymmetric autocatalyst. And from extremely low enantiomeric excess to essentially enantiopure amplification was observed in this asymmetric autocatalysis. So this is the example that we measured the reaction time and the product, and using the enantiopure 2-alkyl pyrimidine alkanol with 1 molar %. And these field circles are observed once. After some incubation time, the reaction goes rapid. And by co-work, the physical organic chemist, Dr. Tsukiyama, set the equation, and this is the first order with the aldehyde, and first order with dialkazine, and the second order with zinc alkoxide, pyrimidine alkanol. So 2 molar of pyrimidine alkanol should participate in the reaction. This one. And this is, and also this is one of this one. This is very simple, too simple. The enantiomeric excess of the autocatalyst is 6 to 4 means 20% S enantiomer, 6S and 4R, and when the 2 molar, the SS, when we postulate that SS is active and SR is not so active, so SS produces more of this. So that means that, but very rough model. And also the other, Professor Janko, Michaud, and Thomas Doucet and Donna Blackmond also presented monomer dimer mechanism. And so from now, the application of this reaction to to other things. The first is the chiral recognition. In other words, also the origin of it is related to the origin of chirality. When we put chiral material, this is 2-butanol, 2s configuration. When the pyrimidine carbonaldehyde and diisopropyl zinc is reacted in the presence of other chiral material, in this case, in the presence of S2-butanol, but with very low, 0.1% EE. And then the product, we thought that the newly formed product should be influenced by this chiral material. It should not be racemic, influenced. And then, once pyrimidine alkanol of zinc alkoxide is formed in the flask, after that the amplification by autocatalysis should work, and we can expect the highly enantiomer-enriched pyrimidine alkanol. So in this case, we got S-pyrimidine alkanol with S configuration with 73% E. On the other hand, in the presence of R2-butanol, we got the R enantiomer with 76, with increased enantiomeric cells. So let me show you the very extreme case, very strange extreme case. This is the chiral hydrocarbon, saturated quaternary hydrocarbon with ethyl propyl butyl hexyl methane. This is the structure R and S. This is the quaternary hydrocarbon and without any unsaturated bond. So this, theoretically, this is asymmetric carbon, R and S. But practically, this has no so measurable rotation of plane polarization, no measurable alpha D value because the structures of the substance are too similar. It's very difficult to distinguish. So this type of this was reported by Professor Weinberg, and this Professor Misro called this type of compound is a cryptochiral. It should be chiral, but we cannot judge which is R or which is S. Cryptochiral. And we synthesize by separation and this compound, and in the presence of this R quaternary saturated hydrocarbon, the reaction between pyrimidine carbonaldehyde diisopropyl zinc gave the S pyrimidine alkanol with high E. On the other hand, in the presence of S enantiomer, we got the opposite, R pyrimidine alkanol. And then another example is this one is the benzyl alcohol. One of the hydrogen atom of the methylene group is substituted by deuterium. So this means the H and D are isotopes. So this is the chiral benzyl primary alcohol. And this, in the presence of this S enantiomer, the reaction gave the R pyrimidine alkanol with 96. On the other hand, in the presence of the opposite enantiomer, we got the S opposite enantiomer. Then of course, the weight of the hydrogen and deuterium is twice. Deuterium is twice. The weight is very different. But let me show you more subtle expression. Subtle means that differences. This is the carbon 12 and the carbon 13. Of course, those are isotopes. When this methyl, the carbon of methox is substituted by carbon 13, this becomes chiral compound in a similar manner this one. And this was the asymmetric absolute configuration of the asymmetric carbon atom was reversed by the Mitsunobu reaction, and this is R and this is R. And you see this is the NMR. This is normal the compound. This is a 2-methoxy group, and this is this is the carbon 13 substituted. 1-methoxy and carbon 13 methoxy is split. This one and this one. And the enantiomeric excess of these compounds were easily determined by NMR. By spectroscopy, we can judge this rather easily. This was derived into MTPA-SL. This one is MTPA-SL. And also the same MTPA acid part. And then this is the S, and this is the R. Those are diastereomers. And the NMR shows, exhibits the signals, this methoxide here, and carbon-13 methoxide, this and this one. And on the other hand, another diastereomers, this one. These clearly show the diastemeric excess is greater than 95%. 95%. So it is easy with this compound to determine the enantiomeric excess by using NMR technique. But so in the presence of this chiral alcohol, due to the substitution of carbon-13, the reaction between the pyrimidine carbaldehyde and diacetylbenzene gave the S-pyrimidine alkanol, while in the presence of the opposite enantiomer, we got the R-pyrimidine alkanol. So this one is a very, but also we have another example. These are the phenyl, normal phenyl, and also the carbon-13 substituted phenyl group. Those are also the enantiomeric compound. Those act as chiral initiators in this reaction. So in this asymmetric autocatalysis, even the carbon-13 substituent can act as a chiral initiator. And as you know, the content occurrence percentage of the carbon-13 is rather 1%, because we often use the measure the carbon-13 NMR. But so far, the substitution, the chirality due to the substitution of the carbon-13 in various compounds have been almost neglected. But this shows that those are also important. Let me show you another aspect of when you get the R product. Let's imagine the chiral pool of the chiral catalyst, ProR, which produces R product, and also the achiral catalyst. So achiral catalyst, of course, produces racemic compound, and the chiral catalyst produces this ProR produces R compound. So the overall of the configuration of the product should become R, regardless of the enantiomer selectivity of ProR catalyst. But however, I would like to show this is not the case. Combination of the ProR and achiral catalyst sometimes produces the opposite enantiomer of the S configuration. This is the example. This one compound 1R2S dimethyl norepinephrine. This acts as a chiral catalyst to produce R enantiomer. This R enantiomer. When this 1R2S dimethyl norepinephrine is used in combination with achiral NN-dibutyl amino ethanol, this is achiral beta amino alcohol. The absolute configuration of the product is reversed. The S reversed. This is the signal. This one is that when we use the dimethyl norepinephrine with R1R2S, the product has shown the R, and then we put achiral dibutyl amino ethanol, mixture of 50-50, still the R was formed. But however, when at this point, 70 to 30, the absolute configuration of the product suddenly reversed to this opposite level. And also the opposite phenomenon was observed by using the opposite enantiomer. And also this is very unexpected result. So we recently examined so the reason is that because the chiral and we adopt the Professor Kaga's model, that's ML2, M2L2 model. The combination of chiral and achiral aggregation, chiral and achiral catalysis, which produces the opposite enantiomer, should work. And before that, should work. And this was the combination of the experiment and also simulation. This is the initial, in the initial stage, this is the enantiomeric excesses. When the 50% is almost zero, but here you see the enantiomeric excess becomes the opposite. So this is only the initial part, and so the enantiomeric excess is very low, but after that the asymmetric autocatalysis with amplification chirality enhances this enantiomeric excess to almost enantio pure. So this is that, and this is the field circles are exact observed result. So that we set the simulations and key value by equilibrium, and also the enantio selectivity of these. This is the opposite one, and so that means that we set about the opposite enantiomer selectivity 10 to 20. So this curve fits rather well. So this result is just published in JACS 2 weeks ago. Here the main topic here is that biological homochirality is a very interesting problem, and there are several theories that propose that the origin of chirality or organic compounds, and usually those proposed theories can give only tiny enantiomeric imbalances. So the problem is how to combine those tiny and those highly enantio enriched compounds in nature. So I'd like to show this possibility of this, but possibility also that the application of asymmetric autocatalysis with this proposed mechanism. First, the circularly polarized light, and some of you are more familiar with it. From the light, when star formation region in Orion, the up to 16 or 17% of light is circularly polarized. This was published in this paper. And of course, the one direction and also the opposite direction, the circularly polarized opposite direction is observed. And circularly polarized have been known for many, have been proposed as an origin of chirality, and it has been used to induce chirality in organic compounds, and especially for asymmetric photosynthesis of hexahelicene. Professor Kagan is here. Is reported, and also from Calvin's group, so independently is reported, and in other cases, so less than 2% enantiomeric excess was induced. So it is sure that the circularly polarized induces enantio enrichment, but also the degree of enantiomeric excess is not high. So we use the circularly polarized, I talk about direct irradiation of CPL to asymmetric autocatalysis. So we prepared the racemic pyrimidine alkanol, and to this, the circularly polarized light was irradiated, 313 nanometer, left irradiation of left-handed CPL, and then the rest of the material was used as an asymmetric catalyst. And then we got S-pyrimidine alkyl with very high E. And on the other hand, irradiation of right-handed CPL gave the R pyrimidine alkyl. And those LR gave SRSR. So this shows good, nice reproducibility. And of course, this 85 and 82% E can be further amplified by consecutive asymmetric autocatalysis to greater than 99.5. So that's 99.5% E. The rationalization is as follows. You see, this is a CD spectrum of the pyrimidine alkanol. You see, this is R pyrimidine alkanol, so this one. At 13 nanometer, R alkanol shows plus cotton effect. This means that R alkanol absorbs epsilon left CPL preferentially. That means the irradiation of left CPL is absorbed R enantiomer preferentially and to convert itself to other compounds to destroy to photo degradation. And this means that irradiation of left CPL should remain more of S enantiomer, and this enantiomer pyrimidine alkanol increase by the mechanism of asymmetric autocatalysis. This is the rationalization. And now this is another aspect of the reaction. There are a chiral organic compound which produces chiral crystal. They are only chiral when they form crystal. And those kinds of chiral crystal have been used as a reactant. But this is Professor Rahat is a pioneer this to get the highly enantiomer enriched compound, especially was the alpha beta unsaturated ketone chalcone type chiral compound. This. And but that is the chiral crystal is used as a reactant. So that is more strictly speaking this is the stereospecific reaction. And so we try to use those chiral crystals as the chiral inducer of other reaction, and in conjunction with asymmetric autocatalysis. This is one example, the N-benzoyl glycine, hyperic acid. This is not chiral, but when it is known, it forms crystal, single crystal, it becomes chiral crystal. And the CD, powder CD, we measure the CD, powder CD, up to 60 nanometer plus or minus, this plus or minus, single crystal. And then, in the presence of those, for example, in the presence of N-benzoyl glycine with plus plus cotton effect, the reaction gave the S-pyrimidine alkanol with high E. On the other hand, in the presence of the opposite enantiomorph crystal, we got the opposite enantiomer. So also this shows nice reproducibility. And another example is that but here, of course, the amino acid and the sugars here are the essential compounds in nature. Both are chiral, and so we want to know the origin of homochirality of amino acid and also sugars. But I'd like to point that also this one, this is not chiral, of course, but this is the cytosine and very important base of the nucleic acid. So this is also the very important biotic material should be. But this is a flat molecule, but so this is not chiral, but this when it crystallizes, it forms either a P or N crystal. It crystallizes from when it is crystallized from methanol, the P plus or minus. This is a powder crystal, CD crystal. The 310 nanometer, either plus or minus cytosine is observed, and is obtained. And in the presence of plus cytosine, the reaction, the same compound, pyrimidine carbaldehyde and diacylglycine, gave R pyrimidine alkyl. On the other hand, minus crystal gave the opposite, S pyrimidine alkyl. So the flat molecule cytosine, when it forms crystal, can act as a chiral initiator, at least in this reaction. And also this is the quote we also use some. We enjoyed Dr. McBride's talk yesterday, and we used the synthetic quotes, D and synthetic quotes. And nowadays, synthetic quotes have been very used widely as a mobile phone or as quote watch, and this one. And we use the powders. But I'm delighted to say that I was very impressed by Professor McBride's talk yesterday, that in the same cave, distribution of D and L quotes is biased sometimes. That's very interesting to me. And in the presence of the powder of D quotes, here, L quotes, the reaction gave the R pyrimidine alkyl with 95, and in the same series B, we used exactly the same reaction equipment, the reaction flask. We just changed the sample of the powder, and then L gave R, and D quotes gave S, D quotes S. In other series also D gave S, and L quotes gave R, so the powder works. And also this is the reaction in the presence of the sodium chloride. We reported the reaction, this one, and D sodium chloride gave S alkanol, and L sodium chloride gave R pyrimidine alkanol. And this is the achiral ionic, the crystal structure Na plus cation and ClO minus ClO3 anion. So the cationic inorganic crystal also work as asymmetric initiator in this case. And I also enjoyed Professor Bielman's talk. This one is very. And let me give you one more. This one is the red one. Red one is the cinnabar. This is also mineral cinnabar, and this one is rather soft. And this powder have been used as the color of the stamp in Oriental world, also Japan, and also this is the HGS helical structure. Then we determine the absolute configuration easily by X-ray crystallography, and in the presence of N crystal, the reaction gave S pyrimidine alkanol. On the other hand, P crystal, helical crystal, gave R pyrimidine alkanol. So the last topic is the spontaneous absolute asymmetric synthesis. This is essentially the most important or most difficult problem. This I showed in the beginning of my talk, that without the intervention of chiral substance, the probability of right side attack and left side attack is 1-to-1, and we get the racemic compound. But however, when from the standpoint of the statistic, the racemic does not necessarily mean the number of molecules S and R is exactly the same. If you toss the coin 100 times, you can get only for 8% probability that you get 50 heads and 50 tails. And tails, and this row pointed, and also seagull pointed this part, and this one is so if you toss the coin 100 times, 50 to 50 is only 0.08, and in 90% of 100 trials, you will get between the 42 to 58, 42 to 58. This means that so-called racemic mixture, so the number of molecules should not be the same, but biased. And as I showed you that in the asymmetric catalysis with amplification of enantiomer excess, so extremely low enantiomer excess can be amplified to measurable enantiomer excess. So we tried means that actually we tried for many years. The first one we published the asymmetric catalysis in the end of 1997, but at that time also we were dealt with this compound and we applied patent in the beginning of 1996, and this was open in 1997. So without adding chiral substance, the reaction between pyrimidine carbaldehyde and diacylprotozine gave either S or R enantiomer with measurable EG. But we repeated the reaction and either S or R. And we found that especially in the presence of the, when we use the ether, this is alkynyl pyrimidine aldehyde, and ether and the toluene solution of diacylprotozine, we got the good stochastic distribution of the formation of S and R enantiomers. S and R enantiomers, 51 to 49. And so this shows this result satisfies one of the conditions necessary for spontaneous absolute asymmetric synthesis. And also, in the presence of silica gel for laboratory use, just silica gel, the reaction of pyrimidine carbaldehyde and diacylprotozine toluene S or R pyrimidine alkanol. In this case, 45 to 39 distribution. So these results satisfy the conditions necessary for spontaneous absolute configuration. And it's very difficult to prove that there's no chiral material. But the outcome, when we can measure the outcome, that means the distribution of the formation of either S or R enantiomers. When it becomes stochastic, so we imagine or we think that this is the result of the statistical fluctuation, the initial statistical fluctuation. So let me summarize that the pyrimidine alkanols and highly enantiomer selected asymmetric photocatalysts, also this quinoline alkanol works. And the amplification of enantiomeric excess from extremely low to essentially enantiomer pure can be achieved. And also this reaction can be used to detect the chirality or to discriminate the chirality. In other words, the origin of chirality, to examine the origin of chirality. So the circularly polarized light works, and also the quartz, sodium chloride, also the cinnabar works. And also the spontaneous absolute asymmetric synthesis. And we believe so. That reaction is spontaneous absolute asymmetric synthesis. But we say scientifically this is satisfy the conditions necessary for spontaneous asymmetric synthesis. And again, this one is Dr. Kawasaki is in the audience, and also Dr. Francois Lutz from France did the kinetic experiment and the calculation, and also many graduate students. And finally, thank you for your kind attention.
Thank you, Soai, for this stimulating lecture. Many questions.
Okay.
the benefit of those who missed my first talk nearly 2 weeks ago, I just want to mention that if you're considering circularly polarized light in the cosmos, you ought to also consider what's called the magnetochiral.
That's it.
That's unpolarized light,
Yeah.
propagating parallel or anti-parallel to a static magnetic field.
Yes.
It's a truly chiral influence. And it can induce absolute inertial selection. This has been shown by Wicking, for instance.
This is,
A magnetic field alone can't do it, an unpolarized light can't. Since magnetic fields and unpolarized or arbitrary polarized light are much more ubiquitous in the cosmos than circular.
Okay.
Although the effect is several orders of magnitude smaller than circular polarized, it's worth considering because you've shown us that tiny anti-magnetic sources can be amplified. Instead of using circularly polarized light as the trigger for your experiments, it might be worth trying unpolarized.
Is how should the strong the magnetic field should strong? That's
Well, as strong as possible.
as strong as possible.
One or two tests. You didn't use a superconducting magnet. Just one or two tests.
That's 1,000 times what it is on Earth.
No, but this is.
Where was magnetic?
Axel is an expert on cosmic magnetic field.
Yeah, but you've got to have it where the chemistry is.
But it's everywhere, you see. This is the point. It's ubiquitous in the cosmos.
Yeah, but these chemicals are not ubiquitous.
And may I ask a very may I ask a very small question? Is it possible to use plain polarized light with magnetic field?
Yes, that would do just as well. The point is you don't need circular. You don't need circular. Arbitrary polarization. So that makes it much more ubiquitous.
Okay. Another question.
Your last slides were nearly last. Did you ever see domains forming, or did you mix the? You've always got resolution into one or the other.
The formation of S1.
Did you ever see domains forming?
Domain means the imbalance.
Half of the sampling was one, the other half was the other. Or do you mix it up to so that can't happen?
In one sample, that is. That one sample has a segregation into.
It's not possible.
That is.
Not in the chemistry.
Well, it's particular mix.
Have you ever done?
Material chemistry perhaps, but
Have you ever done a couple? Have you ever done an experiment with two chambers loosely coupled together to see whether they can?
You see, without starting.
Without
That's
stirring.
when, I see.
I mean, because in reality, domains might be a big effect. And then if you go one left domain, one right domain, then
Thank you for
what happens is how they interact afterwards. And it isn't the original resolution that matters in this reality.
something like that.
On Earth, it may be that there was a left-handed resolution in Stockholm, but a right-handed one in Denver. And the end result would be, who knows?
Other question on the polarized light. Ivo, you have a question on the polarized
No, I
light?
was using the barrel, but was asking something. In this cryptochiral compound, the vibrational circular equation is detectable or not?
So, no, probably not.
Probably not.
But it's worth, but again, this technique I'm going to talk about tomorrow, Raman optical activity, probably is, you could detect a signal and determine the absolute.
Because it is not
that
detectable in the electronic spectrum, but in the vibrational spectrum
Yeah.
can be detected?
Yeah, well, it probably can, nobody's tried, but it's
This one?
something to try.
This one? See that is. See that is. This one.
On the polarized light, related to a polarized light. Günther?
No, it relates
basically isotope effect is
Oh, whether the two don't mix together. It's quite complicated. Polarized light.
So with polarized light, apparently there's frequency dependence and there's cancellation, isn't that right? That's what you showed. So certain frequencies actually give the opposite effect.
It adds up to zero.
This one.
No, it's not.
It's not zero, is it?
Exactly. But if it was
This one.
constant spectrum,
Yeah.
it would add
They
up.
mean, this plus or minus.
Yeah.
Exactly. That we are trying to it was 313 nanometer very well, and so as you see this 240 nanometer, the cotton effect is the opposite.
Mhm.
So we are now using, but the anisotropy factor, G factor, with this is small, so it's not yet successful.
Except
But
today the polarized light is in IR frequency.
Yeah, but there was a discussion in the literature between Mason and Bonner, because Mason also pointed that point that if you change the wavelength, maybe you change that, and if you, but then Bonner made some calculation about it, and he found that a certain range, you have still an effect with the polarized light, and therefore his reaction with the DL losing the work. But if you work it with a monochromatic light, then it's no problem.
Günther.
I have a question concerning the chiral symmetry ranking and the chiral bias in such situations, clarification and on the statistics. Okay, you showed a wonderful example where iso derivative, which one of the primary hydroxys were labeled with a 13C, led to one sort of enantiomers of your organism, but the other one, the enantiomers led to the other. I have the question: if the energetics of the chiral bias is, let's say, much lower than a few small calories, is it reasonable to expect that a single experiment gives you the answer whether this drives positive or this drives negative? So the question is, how many experiments do you usually perform and to decide whether
Oh yes. Okay. You mean the difference due to the carbon 13 and carbon 12 is very small. So of course we repeat, and also that I show here only two chiral materials, but we have another two different type of chiral initiators due to the carbon 13. And with this compound, so it's okay, so it's at least each 10 times, but it is reproducible. And we so far, of course, also from now on, we publish only after making sure that the one enantiomer on the opposite enantiomer gave the opposite direction of the S and R enantiomers. And that means that we don't publish means that after only doing one of the enantiomers, we always do the opposite enantiomer to make sure that the outcome becomes the opposite.
Yeah.
This is really amazing that you can amplify such modest effects. And many people would not anticipate that such a thing would work. So there may be other things in there that we don't know about in your hair or something. So it must not only be that it's possible to amplify this, but if it changes when you use the other enantiomer, it must be that it dominates whatever else is happening in there. So I wonder whether you ever compete two things. So you add quarts of that would make one hand and isotope that would make the other, and see which one wins.
Oh yes, that's also a very important suggestion.
Because it has to do with things you don't know about.
that's what we, as I showed, that one is the, this, excuse me, this is the, maybe this is the slightly different, the answer that you asked me, but the combination of some competition of chiral. This is a chiral, but even if the presence of the a chiral material, so the outcome is reversed.
Another way to ask my question is, what do you do to make sure that there can be nothing else in there?
Okay. I see. I understand. I see. I see. And
how do you purify your glassware, your solvents?
And we cannot say there's nothing chiral. There's nothing chiral because we cannot say. But we can only say
that's more important than the C13, C12.
That is that is okay. If there's any, a sort of we cannot say that there's no other material. But when we put S compound or R compound, and then the outcome is the opposite, and that it is reproducible. So
that means that effect of C13, C12 is bigger than all the other things that might be doing it that you don't know about.
The effect of the chirality of due to the C13 is more stereo directing, more stereo dominant. So that is
It is a solution. Oh, Mer. Just explain. Mer and then like 7 and then you.
There is something, keep thinking of this reaction, the C12 and 13 like mobility there. And I also don't understand what is the effect of the crystal that you are using. Are these things linked somehow to the surfaces of the quartz or of one of these organic materials, and then your cluster is formed actually on the chiral surface of the system? Or, when looking on these C12, C13 experiments, that sometimes the chiral molecule somehow organizes the liquid. The liquid, which is organized, somehow organizes your clusters. You give some elements in the cluster, and then this is what you can amplify by this non-linear process that you find later on. So the question is, do you feel something about the crystals? How the crystals affect, how quartz and kinabab and all these systems affect your asymmetric reduction?
And so for the effect of the crystal surface, there are two mechanisms may be possible. One is that when the pyrimidine carbohydrate coordinates to the surface of the powder quartz. The quartz is the single crystal of the silica gel, SiOH, silano, slightly acidic. So it is sure that the pyrimidine carbohydrate somehow coordinates. And pyrimidine carbohydrate has two enantiomer faces, like D and C faces. And when the quartz is chiral, so there's maybe some difference. Some differentiation.
But you also described this experiment by taking this amorphous silica, which had a chiral morphology. And then the question is that if it is absorbed on this amorphous silica, which is not chiral, is only the morphology is chiral, how this operates?
Amorphous silica is we use, that's just the slightly acidic accelerator. The aldehyde, when this coordinates to the oxygen of aldehyde to accelerate. And also, may I answer your first question that one is that aldehyde coordinates to the chiral surface, so B phase or D phase differentiation. Another mechanism may be that when the pyrimidine alkanol, zinc alkoxide of pyrimidine alkanol is formed, of course, so probably the enantiomer excess is very low. So one of the enantiomer is inhibited, it is coordinated to coordinate to chiral material, and the rest of the enantiomer amplifies. That is also possible, but we don't know which one works.
Because if your experiment with the C13, C12 works, it must be some kind of modification somehow of the liquid. And the liquid might have some kind of chirality
Well,
where it causes...
yes, and C30 substance, the reaction is homogeneous. Yes. Yes, the reaction C13 is the reaction is this one is a homogeneous reaction. Yes. And as you see,
I want to inform you that the coffee shop is closed, far away. But another question from Axel, then another one from here.
Just to emphasize again, yesterday we saw that in the crystallization experiment, we always, in the absence of any artificially impurities, we always had, I think it was right-handed in your experiment, and it was done in 4 different labs around Europe. Whereas in your case, you're very close to zero with your impurity.
That is
And I think that is amazing. But you could probably try to measure by how much of an impurity or how much of a perturbation is sufficient to tip it systematically one way or the other. Because you can put your initial enantiomeric excess down to 10 to the minus 4 or 5. And at some point or the other, you must find the watershed between tipping it systematically to the left or systematically to the right. And that would quantify perhaps the laboratory offset that you might have. And in the other case, it was amazingly close to zero, amazingly off.
And also they used to talk about crystallizing. This is not crystallizing.
No.
This is essential. Essentially.
Still, in both cases, of course, both handednesses are possible. And you could tip the direction with small perturbations in either direction.
Thank you. One question?
Okay, that's a quick question. Also, you made it about when you have duality, that you completely switch your duality as star. And how did you explain that? Because that's for me.
And just a moment, I explain this one is so this is the experimental result. Okay. This is after you see the enantiomeric excess is very high. This is due to the amplification by the mechanism of asymmetric autocatalysis. So we postulated, that means that we adopted Proust-Kagan's model. That means that the chimeric model, that this was chiral and achiral aggregation acts as a catalyst to produce the opposite enantiomer, to produce the opposite enantiomer.
So you mean when in the transition state, you switch the side, you block one side.
And also that there's the equilibrium is equilibrium. And equilibrium, that means the amount of this and this and also this change. This is a simulation. And these black field circles are observed experimental results. And when we postulate the equilibrium, this one, and VC means the aggregation of chiral and achiral material, which produces the opposite. And also this enantiomeric excess is not very high, to 10 to 20. So in this case, this called red one fits. And also this is the reactivity. But let's see, please answer. This is only the initial period of the reaction. This is the reactivity simulation. And without the Kaiser, without the equilibrium, something happening with this one, or also with shrinkage. So this is roughly This means, as you know, the enantiomer selective addition of dialkyl zinc to aldehydes catalyzed by beta amino alcohol. Professor Kagan's talk, the Professor Noyori postulated single type monomer catalyst. But this result, the reversal of the enantiomer selective, cannot be explained by the mono catalyst. And then we should adopt
So I was wondering,
and
I
then,
think that it could like change somehow like the environment itself. It's homogeneous.
this is homogeneous. Yes.
Last question.
Okay, could it be that you are dealing with different stoichiometries in your complexes? So, as far as I see.
Pardon? What is different?
Could it be that you're also dealing with different stoichiometries in your complexes? So instead of, let's say, having 2 to 2, something like 1 to 2 and 1 to 3, and then this explains, let's say, the space diagram you see by means of measuring the alternating.
Do you mean 1 to 3 means 1 to 1 and also 2 or something?
Yeah, something like this.
3
Because here you have always 2 to 2.
This
Let's
is
say 1 to 1 situation. In most complexes.
1 to 1 means
But if you have, let's say, a 2 to 1 situation,
pardon, let's see, talk. 2 to is. This is really clear with that. There are 4
Okay.
3 modes. Maybe,
2 to 1 or something
maybe.
like this, so not even, but odd relationship.
Maybe when we postulate the enantiomer selectivity and also the reactivity of those aggregates, it might be possible, but we have not yet done that simulation. But it could be.
Last question. No, last question, and then 10 minutes. Go on.
I'm also puzzled about the stereosymmetricity of the crystals. So I was wondering, do you perform these experiments in the dark, where you add the crystals, because you showed that it's very sensitive to polarized light?
Polarized light is, well,
Are you making polarized light in situ using crystals? It's only a very weak
this one is the, when we irradiate the polarized light, of course it is dark. It is dark without the influence of art.
Yeah, I mean, with only the crystals. So
Crystal.
the quartz, for instance.
Crystal and
Do you do that experiment in the dark?
crystal, the quartz,
Yeah, for instance, where you have several.
When you are working with the sun.
some crystal. You mean the effect of the circular polarized.
No, ordinary light. Through the quartz crystal.
Yeah, and then it falls on the quartz crystal.
It becomes polarized.
You see.
Powders, he's working with powders, not with
Yeah.
crystals. He's working with powders.
It doesn't work.
Oh, I see. Yeah, you're basically so that's it, to make the polarized light, some quartz substances use. Oh, this is in this case that we use the powder. So overall chirality. Thank you.
Yeah.
Okay, thank you.
Thank you.